A DC machine can turn electrical energy into motion, acting as a motor, or convert motion into electricity, working as a generator. This dual functionality makes them extremely versatile and valuable in countless applications. The DC stands for direct current, electricity that flows in one steady direction, unlike alternating current or AC, which constantly reverses direction. This steady flow is what gives DC machines their unique advantages. Unlike AC, which reverses direction, DC is constant, making it perfect for applications needing precise control like cars, robotics, and industrial tools. DC motors are often chosen when smooth, adjustable speed and torque are required. So how does a DC machine generate electricity? It's all about electromagnetic induction, moving a wire through a magnetic field to create voltage. This is the fundamental principle behind all electric generators and motors. This voltage, or EMF, electromotive force, is described by the equation EG = PHZN 60R X PA. This formula helps us understand how different factors affect the output of a DC machine. pH is the magnetic flux, which represents the strength of the magnetic field passing through the machine. Z is the number of conductors or wires in the armature, and N is the speed at which the armature rotates measured in revolutions per minute. P is the number of magnetic poles in the machine, which helps determine how the magnetic field interacts with the wires. And A is the number of parallel paths in the armature winding, which affects how current flows through the machine. Want more voltage? You can spin the armature faster, use a stronger magnet, or add more wires to increase the number of conductors. Each of these changes boosts the output of your DC machine. This equation connects the physical parts of the machine to the electricity it produces, letting us predict and control its performance. DC machines let us see and measure science in action, turning invisible forces into real, usable energy that powers devices and experiments. Whether as a motor or generator, DC machines are essential in technology all around us, from electric vehicles and trains to elevators, cranes, and even toys. Let's open one up and see what's inside. By looking inside, we can discover the key components that make these machines work, like the armature, commutator, and brushes. Get ready for some hands-on science. We're about to see the inner workings of a DC machine up close, so grab your curiosity and let's get started. To understand a DC machine, let's look inside. The yoke, or frame, is the sturdy skeleton, supporting everything and guiding the magnetic field. Magnetic poles attach to the yoke, focusing the magnetic flux. Brushes, usually carbon, press against the commutator, transferring electricity between stationary and moving parts. The commutator, a ring of copper segments, acts as a mechanical switch, ensuring current always flows in one direction. The armature core, made of laminated steel, holds the windings where voltage is generated or motion is created. All these parts work together, turning physics into real-world power. That's the magic inside every DC machine. Let's untangle the armature windings and see what makes DC machines tick. Inside every motor, the arrangement of copper coils is crucial. These windings are the heart of the machine, shaping how electricity flows and how the motor performs. Lap winding creates many parallel paths for current to travel. This design is perfect for applications that need high current at low voltage, like powerful industrial motors. The parallel connections help distribute the load, making the motor robust and able to handle heavy work. On the other hand, wave winding connects the coils in series, which is ideal for high voltage and low current needs. This setup is often used in machines where efficiency and long-distance power transmission are important, as it allows the voltage to build up across the windings. The choice between lap and wave winding depends on the job at hand. Do you need more current or more voltage? When current flows through the armature, its magnetic field interacts with the main field, creating what's called armature reaction. This invisible force can have a big impact on performance. Armature reaction can distort the main magnetic field, leading to unwanted sparking at the commutator and reducing the machine's efficiency. Over time, this can cause wear and tear, making maintenance more frequent and costly. To solve this, engineers use compensating windings and interpoles. Compensating windings are placed in the pole faces to cancel out the unwanted magnetic fields, while interpoles are small auxiliary poles that help with smooth commutation, reducing sparking and keeping the motor running efficiently. These clever engineering solutions keep DC machines both efficient and reliable. The right winding method, combined with smart design, ensures that the machine delivers power smoothly and safely. That's how we keep the sparks at bay and the motors spinning strong. Now let's see how all these machines work together in harmony, each one powered by carefully chosen windings and precise engineering. Sometimes one generator isn't enough, so we connect them in parallel. For safe operation, match polarity and voltage, and ensure each generator shares the load proportionally. Compound generators use an equalizer bar to balance the load. Switching to motors. When starting a DC motor, the armature's low resistance can cause a huge current surge. A starter, a variable resistor, limits this inrush, protecting the motor. As the motor speeds up and generates back EMF, the starter is gradually removed. This simple device keeps motors safe and reliable. Now let's compare shunt and series motors. DC motors come in two main types, shunt and series. Each has unique characteristics that make it suitable for different applications, and understanding the difference is key to choosing the right motor for your needs. In a shunt motor, the field winding is connected in parallel with the armature. This design provides a steady, reliable speed even when the load changes. That's why shunt motors are commonly used in equipment like fans, lathes, and power tools, where consistent speed is important for performance and safety. Series motors, on the other hand, have their field winding in series with the armature. This setup delivers massive starting torque, making them ideal for heavy-duty jobs like powering trains, cranes, and hoists, anywhere you need a big push to get things moving. However, there's a catch. If the load on a series motor suddenly drops or is removed, the motor can accelerate uncontrollably and reach dangerously high speeds. That's why series motors must always be operated with a load attached. Speed control in shunt motors is achieved by adjusting armature or field resistors. Interestingly, weakening the field winding actually increases the speed, giving you precise control over how fast the motor runs. For series motors, speed can be adjusted using diverters or tapped windings. These methods allow for some flexibility, but speed control isn't as fine as with shunt motors. Ultimately, the right motor and control method depend on the specific job requirements. Think about the load, the need for speed control, and the environment where the motor will run. Remember, choose a shunt motor for steady, reliable speed, and a series motor when you need big torque to start heavy loads. That's the science behind smart motor selection, matching the right type to the right task for safe, efficient operation. Next, let's talk about efficiency and how it impacts the performance of these motors in real-world applications. How do we make these machines work better, last longer, and use less energy? Let's find out. No machine is perfect. Energy is always lost. Copper losses, I2R, turn current into heat in the windings. Iron losses, hysteresis, and eddy currents waste energy in the armature core. Laminated steel cores help reduce these losses. Mechanical losses come from friction and air resistance. All these losses add up, lowering efficiency. A well-designed DC machine can be over 90% efficient,